Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book, three-volume series I wrote from 2019 to 2022. It's available on Amazon.com in both Kindle and paperback format in case you're interested in purchasing a copy of any one of these volumes or the whole set. Anyway, today I'm starting a new chapter, and that's on computation. And I'm just going to start with the first section, which is what is a computer. So, anyway, let's get started. So, yeah, like I said, I'm starting a new section on computation. And maybe before I explain what a computer is, I should explain a little bit about computation. Computation is just a mechanical method for solving problems. I'm sure you guys all know this. I mean, we live in the computer age. I'm sure you're all familiar with various forms of computation. It doesn't even have to be done by computers. I mean, people have been doing computations as long as they've been doing math. It's just the way you solve math problems, really. But there's a method to it. I mean, if you're going to mechanize computation, you have to have a systematic method for solving problems. That's called an algorithm. So, algorithm is just a set of specific instructions for solving a particular type of problem. It doesn't even have to be a math problem. It could be a practical problem involving something else, but ultimately the steps all have to involve, mathematical operations or logical operations. And that's exactly what computers do. So that's why computers are useful tools. Computers are basically hardware, technology that we use to mechanically perform various types of computations. That's what computers are. And now I'm talking about what is a computer. And most people say that computers have five components. This is how I learned it anyway. Here's a little diagram of what a general computer. I think all computers have these five components. Now we write them usually as three components, but they all have an input. And I think you guys are all familiar with input. That was for most computers, PCs, or laptops. That's your keyboard. Your keyboard is your input, or it could be your microphone or your mouse. If you're just clicking things on the screen, you have a graphics interface, a GUI. That's your input. Anything you tell the computer to do is your input. Uh, and then what does a computer do once you give it your input? Well, it processes the input. And it has something called the central processing unit, or CPU for short. Um, and I'll get into that in more detail in a minute. But it does a bunch of processing. You give it an input. So, for instance, a very simple example. Suppose you want to tell get your computer add 2 plus 2. So your input might be just the string 2 plus 2 and return, and then the computer does some analysis on that expression, and hopefully it'll give you the right answer, which is 4, and that's your output. It'll output that usually on your screen, or if you wanted to print out, it can output on your printer, whatever your output device is that you want the computer to spit out the output. And of course, usually you do problems a lot more complicated than 2 plus 2, but I think you get the idea. So, how does a computer work? I mean, I told you what it does. I told you that it takes an input, processes it, I guess it calculates the answer, and it gives you an output. But then the way it does the processing is done by the CPU, and there's three components of the CPU. There's the memory. Every computer has memory. It has to store the intermediate results that it's using. So memory in a computer is usually a bunch of locations where you store these binary numbers or hexadecimal. I think nowadays most computers, most PCs use hexadecimal or hex because it's a lot more compact than binary. Anyway, they have different ways to store data, and you have a bunch of memory locations in your CPU, and in each of those locations there's a number, usually represented in hexadecimal. And then you've got a control unit That is actually what does the computation. Or no, actually ALU, the arithmetic and logical unit is the part that does the calculations, does the number crunching. The control unit is what reads in a program, and the computer can't write a program itself unless it's a really super sophisticated computer. Most computers don't write their own programs. That's up to the programmer. The programmer also feeds in a program to the computer. That's the algorithm I was talking about. So it's not just enough to just give it an input. You have to give it a program too. And it could be a program you've downloaded on the computer, like Mathematica. I have Mathematica on my computer, but that's part of the control unit. I'm running a program. Some programmers spent the last close to 20 years writing code for Mathematica. I was actually one of them. I was a kernel developer at Wolfram Research. They make Mathematica. I was there for 3 years, from 2000 to 2003, and I actually did write some code for Mathematica. In particular, I wrote code to factor integers much faster than they were being done before. I implemented very fast algorithm for factoring large numbers known as a quadratic sieve. Before I got there, they were using a continued fractions method, which was about 50 times slower. So I did improve their factoring code quite a bit when I worked there, and I worked on a lot of other stuff as well. I mean, to toot my own horn too much, but dozens of other people, maybe hundreds, have worked at Mathematica to develop all the rest of their code. So it's a very complicated program, but it can solve mathematical problems, some pretty complex ones. And of course, there's a lot of other types of programs you can run. You can write game programs. You can run programs to do anything you want on the computer, but they're all programs, and they all take an input, and they all spit out an output. So then you have to run your program. Once a program's written and there's no bugs in it, meaning it works properly. And by the way, debugging is one of the hardest parts of programming, getting it right. Kind of like Thomas Edison said, well, genius is 1% inspiration, 99% perspiration. So programmers do a lot of perspiration, and that's called debugging. But at some point, hopefully, they get their code right and it works properly, and then you can run it. And once you run your program with your input, it'll give you the output. It'll tell you the answer to the problem that you want to solve. And once it solves a problem, it outputs it. You can tell it where to send the output. That's part of the program. You can either tell it to output it on your screen, or you can usually it's on your screen, and then if you want to print it out, usually you have to use another program, sort of the front end program on your computer to print what's on your screen. That's another program. But you can get your output to go to any output device you want. So that's how computers work. They all work this way, no matter how primitive they are. Even the first computers ever built. And by the way, the first computer ever built, the first electronic computer, was called ENIAC, and that was built in 1945. I think right at the end of World War II. So we've had computers for a long time. We've had electronic computers for 80 years. And of course, they've gotten a lot faster and a lot more sophisticated. We didn't have PCs, personal computers, until the mid 70s. I didn't get my first PC until 1984. That was an IBM PC that used DOS, and it was, very hard for most people to use. But now, pretty much everybody's using computers or smart devices. Smartphones are really just an example of computers, but they're on your phone, and they run a lot of different apps or programs on your smartphone. So now we're all using computers all the time, and we don't even usually call them computers anymore, but that's what they are. Even smart watches and smart rings. Just to give you an idea how much faster and more powerful computers are. You probably know about Moore's law. Moore's law, and it was true. I don't think it's true anymore, but for about 70 years at least, from the beginning of the computer age, I think for around 80 years, from around 1945 to maybe around 2020. I think that was when we reached the end of Moore's law. for about 75 years, every 18 to 24 months, computers were getting about they were doubling in speed and in memory, which means that in that period of 75 years, they got about a billion times faster and could store about a billion times as much information. Pretty amazing. I mean, now I think a smart ring has more computing power than most powerful computers in the world did in the 1960s, including the ones that sent the astronauts to the moon. Pretty amazing. But anyway, that's kind of an overview of computers and what they are. Actually, maybe I should say a little bit about programming languages. If you want to use a computer, if you want to use I mean, we all use computers, but most of us don't write our own programs. If you write your own software, you're what's called a programmer. And to be a programmer, you have to learn one of these programming languages. These are, I think, 14 of the most popular programming languages today. I know about half of these. The one I think is the best of all these is C. And there's a couple offshoots of C. There's C sharp and C plus plus. I'm not all that crazy about C sharp, but C plus plus is pretty great. That's an example of what's called an object-oriented programming language. That's kind of a newer style of programming that kind of got started in the 90s and very high level. One thing that's happened with computer programming, it's become more and more high level, which means it's become more and more like English. It's simpler. I mean, I don't know if it's simpler because these are some pretty complicated programming languages, but at least it's easier to kind of understand how to write code for computers these days. You know, in the old days, I think until I think Fortran was the first high level computer program. That one's not even listed here. Fortran's archaic. I don't recommend Fortran, but it was very popular for a really long time, starting in the 1950s. But before Fortran, people were just doing machine language. They were literally just feeding bits and bytes of information into the computer. They were writing all their code in binary, which was a pain in the ass. I've never done that. I mean, there is something kind of close to that. It's called assembly programming, which is kind of computer hardware programming. I haven't done too much of that. But all these are high level languages, and they all have commands that look kind of like English. And I like programming. I mean, I think it is, I think not that many people know how to program. I'm guessing maybe about 1% of all the people in the United States probably know how to program a computer in one of these languages. Maybe it's a little higher than that, I don't know. But, you know, it is a good thing to know. I think it'll help you get some good jobs in software engineering. I did work for about 9 years full time in software engineering. So I am a programmer and I do it on my own, and I really do enjoy programming. Um, I like working with computers. I like computers. Not everybody does. A lot of people are scared of computers. I'm not. I'm more scared about people, if you want to know the truth. Yeah, and I kind of agree with what Hal said in the movie 2001: A Space Odyssey. Whatever problem he had was due to human error. I think most of the problems we've had with computers have been due to human error. Computers just do what you tell them to do. At least today they do. And, I mean, they're just following instructions. So whatever a computer does, it's not its fault. I mean, maybe the software is not working properly, maybe the hardware is not working, but that just means the computer's broken. It's not functioning properly. It doesn't mean it's evil. It doesn't mean it's thinking for itself. It has some evil plot, which is kind of the plot of a lot of sci-fi movies. I just don't believe that. So people who program it, you can write programs to do evil things, but the people are the ones who wrote those programs. Computers didn't think of them. So anyway, maybe enough preaching about that. But anyway, that's kind of an overview of computers and what they do and computer programming. And that concludes my video for today on computing. So thank you for watching. Long live math, and I'll see you guys next time. Bye.